Hello everyone, this is the last of the video lectures on electrical circuit, and we are finally talking about circuit connections. In this video, our goal is to compare the total current that is passing through my resistors, or the amount of current that is passing through my resistors if they are connected in series versus if they are connected in parallel, as well as how much is the voltage drop or how much is the decrease in voltage when my resistors are placed in series and again when they are placed in parallel configuration. So those are the things that you are going to compute and understand in this last video lecture. In our previous discussions, we use the water circuit analogy to understand the electrical circuit better, right? So what you can see here, or what I want you to first remember, is when we talk about the circuit, it's a closed system. It's a closed connection that looks like this. So in this scenario, my water is contained in a closed unit. So it is just going up and down and going up and down in a cycle through the pipes like this. Okay, so obviously in this analogy, my water that is flowing is analogous to the current, right? In some areas or some sections of the wire, they are narrower because there are water bulbs that are present in these sections. These are my resistors, or this serves as my resistances. And the overall effect is it slows down the flow of water. And then we also have our water pump because of course water can naturally fall down or go down from here to here, right? But for it to be a cycle, my water needs to come back up. It can't do that on its own. So you need an external device like a water pump in this situation for you to get the water back up. In our analogy, that would serve as our battery, or that would serve as our voltage source, right? Okay, let's go back to the effect of the water bulbs here on my current or in my water flow. Here, my water bulbs are connected in series. Imagine if we don't have any water bulbs here and that the wires are all same in size. There are no sections where it gets narrower. So what happens in this scenario is it slows down the flow of water that is flowing through your cycle, right? And it is not only slower in this part of the pipe where there is restrictions, where it is narrower, but it is slower everywhere. Okay, that means my current, the amount of current passing through here, if I took a measurement here, is just equivalent to the amount of current or my current that is present on the other side of the wires or of the pipes where it is not narrower or where it is regular size. I guess this is a better way to think about that. Instead of water, think of them as like some sort of like crystals, right? They are densely packed with next to each other, and they are cycling, moving up and down in our pipe system like this. Now here on this section of the wire, it's narrower. So instead of three crystals, it only can accommodate one crystal at a time, right? Because you have this bottleneck situation, it results to a lower flow rate overall, right? It's not only slow here because there's the bottleneck here, but it is slow everywhere. The flow rate is the same everywhere. Another way to think about this is, let's say these are people and they are in some sort of procession. They are going in a circular fashion. back and forth, like in a circuit. But then in this section, the road gets narrower. So instead of three people passing through, you only get um, one at a time, one person at a time passing through. What I want you to realize is it's not only slow in this section, but because of this restriction, narrowing of the road, it becomes slower on the whole procession becomes slower in pace, right? So that's what I want you to realize that when we have a closed system like that, water flow or the current is the same all throughout. So if you take a device that can measure your current, it would give you an equal the same measurement wherever you put it, even on the part where there is a resistor. It is not it is not lesser or slower along water bulbs. The measurement is the same. Okay, now we have something different here. So instead of my water bulbs placed in series, now they are placed in parallel like this. And what we can see here is that my pipe system have three branches. So if I get to this point, the water coming in would be able to have multiple pathways. It can pass through the first branch or the second branch and the third branch, and then again they would all converge here, and they all I guess they all combine here in this pipe. And then this is not a complete closed system, and then it would cycle again. Okay, so in this case, because there are multiple pathways to accommodate your water, you actually get a larger water flow, right? Your water flow is faster. There's more volume of water per unit of time that can pass as compared if you have the three bulbs in series, right? So the effect would be really different if you place your water bulbs in series or in parallel. In parallel configuration, water flow divides into branches. More water can pass through a branch with wider pipes. Let me get back to the illustration. So, although they look the same, just for the sake of argument, let's say this one is a bit more narrower, right? As compared with the second and the third. If this is a bit more, not narrower, a wider, rather, if this is a bit more wider than the second and the third, we expect that more water can pass through, right, on the first branch compared with the second and the third branch. In other words, if we translate that, if this one has lesser resistance, it can accommodate more current compared with the second and the third one. Okay, so more current on the branch with the less resistance. Let's say I have 20 gallons of water here. These have wider pipes. So let's say the water divides into 10 gallons here, and then 5 here, and then 5 here. Okay, so obviously there are more volume that is able to pass here because the pipes are wider, and then they all converge back into my 20 gallons when they get out of the branches. Okay, so in other words, the current is still the same all throughout. It just so happens that here on the branches, you have to add up the amount of water, right? Because it divided, it got divided into the three branches. But definitely the water here before the branch is equal to the water amount of water after the branch. Okay, so this is just about the same circuit that you saw from a while ago. The only difference is now we put our power source or our voltage source right here. And we are going to use the conventional flow of current. Remember that conventional flow of current means that my charges is coming from the positive, coming out of the positive towards the negative terminal. Okay? Remember, in conventional current, conventional direction of flow, what they thought before was it is the protons or the positive charges that are flowing instead of the electrons. That's why they have this configuration. In textbooks, conventional direction is still used. So we will also do that. Here in our circuit, we have a power source or a voltage source, a battery source that gives us 60 volts of voltage gain. And then my current has to pass through two resistors. The first resistor, R1, has a rating of 100 ohms, as well as the second one. How do I represent my current that is passing through my resistor? Like this, through arrows. And I will put a notation here. I1 means the current passing through resistor number 1, and the current passing through resistor number 2. We expect that since the resistors are in series, that the total current would be lesser than if there is only one. Okay, so how do we compute the total current if my resistors are in series? Our formula is the total current is equal to the current passing through resistor number 1 and the current passing through resistor number 2. Again, let me remind you that in a series connection, the current here or a current here or the current along passing through R1 or R2 is just the same. Although the resistors in series are slowing down the current, it's slowing down the total current, not only the current passing through them. Okay, so that's why you get this equation. The total current is just equal to whatever is passing through R1 is the same as passing through R2 and the same as passing through this wire going back to the battery or the voltage source. Okay. Now here is something different. This is a circuit that is in parallel. You have the same rating of battery voltage source. It's still 60 volts. My R1 and R2 are still 100 ohms, but it's arranged in parallel now. We are still following the conventional flow of current. My current is coming out of the positive terminal and then going back to the negative terminal. Now let's analyze this a little bit. Here is my current. When it reached this node, some of the current will pass through this branch, the middle one here, and the other will pass through this branch. Since both of them has equal rating, 100 ohms, we can say that half of the current will pass through here and half will pass through R2. And then at this node, they will combine back again and we get our total current that goes back to the negative terminal. Okay, so how do we compute for the total current? Obviously, it's not the same with series connection. When we have parallel circuit, our computation for total current is different. You have to add. You have to add the current that is on the branches. If you have another branch here, of course, you have I3, I1 plus I2 plus I3 is equal to the total current. Okay? How do you compute how much current is passing through the individual branches? Well, you can still use the Ohm's law. I is equal to V over R. You have N here because I1, if you want to compute for I1, well, I guess you have to use R1, the value of R1 here. If you want to compute for I2, this would be I2 is equal to V over R2.